Welcome. In this video I'm going to show you how to complete the assignment called multiples. Our first problem says a red car travels down the road. A blue car also travels down the road, going twice as fast as the red car. How many times farther will the blue car have driven than the red car in a given amount of time? Now all of us can do this in our heads. We know the answer is twice as far, but let's take a look at the method that we use to get that answer, because this method is going to serve us in the more difficult problems where we can't do them in our heads. Let's start by writing an equation for how far the red car travels. Distance of the red car is going to equal the speed of the red car times the amount of time it traveled. I don't need a subscript on the t because the blue car is driven the same amount of time. Likewise, the distance that the blue car has traveled is going to equal the speed of the blue car times this same amount of time. Let's write this out again, but let's perform a substitution. The distance that the blue car has traveled is going to be equal to the velocity of the blue car, but it tells us in the problem that the blue car has a velocity that's twice as fast as the red car. So we can say 2v red times t. And since v sub r times t is equal to dr, I can simply substitute this with dr. And here I have my answer. The distance that the blue car will travel is twice the distance that the red car will travel. Okay, our question on the third page is identical, except now the blue car is traveling 3 times as fast as the red car. So we have all the same math here, except this is going to be the distance that the blue car travels is 3 times the distance that the red car travels. Page 4 is very similar to the first two problems, except in this case the red car and the blue car are traveling at the same speed, but now the blue car travels for twice as much time as the red car. How many times further will the blue car have traveled than the red car in a given amount of, it should say distance here, not time, because the time is what's different. So let's try this. The distance that the red car goes is going to be velocity or speed, and I'm not going to put a subscript on this because both cars are going the same speed. We don't need to distinguish between the two, times the time that the red car is going. The distance of the blue car is going to be equal to velocity, same velocity as the red car, times the time that the blue car has been traveling. Now the distance that the blue car has been traveling is, its time is actually 3 times the time of the red car. So we can rewrite this as 3b t r. Your math teacher wouldn't be happy with this. Let's move the number out front. dB equals 3 vt r. And we know from earlier that VTR is the distance of the red car. So we can write this as, let me scroll up a little bit. We can write this as the distance of the blue car equals 3 times the distance of the red car. What happened? I misread the question. It's twice as much time. Sorry about that. That changes all of our 3's to 2's. the distance of the blue car is going to be twice the distance of the red car. So by now, you're probably starting to see a pattern. The distance the red car goes is the speed times the amount of time that the red car goes. The blue car was going twice as fast. If we double the speed, what we do to one side of the equation, we must do to the other. We've doubled the distance. Let's see if that pattern can help us in some of the more complicated problems. A red car travels down the road once again. A blue car travels down the road going the same speed. The blue car travels 4 times as much time as the red car. How many times farther did the blue car drive than the red car? So distance equals velocity times time. The blue car is traveling 4 times as fast. That means 4 times the distance. Okay, let's jump to page 8. We're getting into questions now that are not necessarily linear. Brad can accelerate twice as fast as Barney. If each runs for 2.1 seconds while accelerating, how many times farther will Brad go than Barney? We don't need to know the amount of time. We just need to know that in an accelerating system where they both start from rest, our formula is d equals 1/2 at squared. And in this case we are we're doubling the acceleration. We're going to put a 2 in here, and what we do to one side we must do to the other. He's going to go twice as far. Okay, page 9. Just to give Barney a chance, Brad decided to accelerate at the same rate as Barney. But Brad ran for twice as long as Barney, while both were accelerating at the same rate. How much farther did Brad go? How much farther? This is once again a d equals question, and distance in an accelerating system with an initial velocity of 0 is 1/2 at squared. But this time we're doubling the time, and time is squared. So if we double the time, well, that squared goes with the both of them. 2 squared is 4, so we're going to need to put a 4 over here. Page 10 is another nonlinear problem. A rock is dropped from the roof of a tall building. Another rock is dropped from a building twice as tall as this building. How many times longer will it take the rock dropped from the top of the taller building to reach the ground? Now, I know from previous years, most people's first guess would say the building is twice as tall, it's going to take twice as much time. Let's see if that's true. Okay, we're going for time here. There's a formula that we learned earlier in the year, which is our time drop formula. That time equals the square root of 2h over g. And what we're doing now is we're doubling the height of the building. So we're going to put another 2 in here. It's not 22, that's 2 times 2. Let me put a dot there. So if we're going to put another 2 in here, it's a 2 under a root symbol. Well, what I do to one side, I must do to the other. So we're going to say root 2 t. Let's put the t out front. It's a little more readable that way. But we're going to take the, however long it takes, we're going to take that amount of time and multiply it by root 2. Root 2 is something you should have memorized. It's 1.414 in decimals. Let's see if that's the answer. And indeed it is. Okay, question 11, similar to question 10. A rock is dropped from the roof of a 32-meter tall building here on Earth. Another rock is dropped from the top of an identical building on a planet with twice Earth's surface gravity. how many times quicker will it take this rock to fall compared to the rock dropped from Earth? Okay, again, our time drop formula, time equals root 2h over g. Now in this case we're doubling the gravity, so if I'm going to put a 2 in here, I better take my time and also put a 1 over root 2 here. So in other words, to this side, we added to this side a 1 over root 2, and therefore we must divide t by root 2. And in case you don't have this memorized, the square root of 1 over root 2 is 0.707. Okay, on page 12, a rock is dropped from the top of a 30-meter tall building here on Earth. Another rock is dropped from the top of a 30-meter tall building on a planet with twice Earth's surface gravity. So far it looks like the last problem, but this time it's asking how many times faster in terms of speed will this rock fall compared to the rock dropped on the Earth. Last time was asking for time. So how many times faster speed? Well, we learned the drop formula for speed is v equals the square root of 2gh. And in this case we're going to put an extra 2 in front of the g. Let's put it outside. It might be a little easier to understand what's going on. Root 2, what we do to one side we must do to another. I'll keep the v out front. Root 2, it's going to be root 2 times faster, and if you've got root 2 memorized, that's 1.414. 1.414. And correct. Okay, on page 13, we're asked, a rock is dropped from the top of a building. Another rock is dropped from the top of a cliff. The rock dropped from the cliff takes 3 times as long to hit the ground as the one dropped from the building. How many times taller is the building than the cliff? You might be tempted to go with the time drop formula that we had a minute ago, t equals 2h over g, but it's actually even simpler than that, because if you remember where this formula came from, it came from one of our original kinematics formulas, d equals 1/2 at squared. We saw that formula earlier in this assignment. In this case, d happens to be the height, and acceleration happens to be due to gravity. It was from this formula that we derived the time drop formula. We just isolated t, so we don't need to start from here. Okay, what are we doing here? The rock drop takes 3 times as long. Alright, well, we're going to put a 3 in front of the t, but the t is squared, so the 3 must get squared also. What's 3 squared? Well, that's 9. So if we put a 3 in there, we've got to put a 3 squared or a 9 over here as well. So 9 times the height. How many times taller is the building than the cliff? Sorry, how many times taller than the building is the cliff? And it should be 9 times. Okay, page 14. A rock is dropped from the top of a building. Another rock is dropped from the top of a cliff. The rock dropped from the cliff takes 3 times as long to hit the ground as the one dropped from the building. How many times faster speed will this rock be going when it hits the ground than the one dropped from the cliff? Okay, so we're going to need a speed formula in terms of, well, we're not given the height of the building or the cliff, or we're not even given a multiple that the cliff is twice as tall as the building. So how to solve this? It looks like I threw in a linear problem in the middle of all these more difficult problems. So we're going to start by saying the change in velocity equals acceleration times time. Okay, and since these rocks are dropped from rest, the change in velocity simply is the final velocity. We can get rid of the delta. Now if the rock that's dropped from the cliff takes 3 times as much time to hit the ground, it's accelerating for 3 times as long. Acceleration is constant. It should simply be 3 times the speed. Okay, page 15. Looks like we're back to red and blue car examples. A red car travels down the road. A blue car also travels down the road, going 1.5 times as fast as the red car. How many times farther will the blue car have driven than the red car in a given amount of time? It looks like I got nice and just threw in another linear problem for you. How many times farther? Distance equals velocity times time. The blue car travels 1.5 times the speed. What I do to one side, I must do to the other. 1.5 times the velocity. 1.5. There you go. Wanted to make sure you didn't forget how to do the easy ones. Question 16. A red car travels down the road. A blue car also travels down the road, going twice as fast as the red car. How many times farther will the red car have driven than the blue car in a given amount of time? This is just a trick question, which is the same question as the one before. How many times farther will the red car have driven? Well, the red car is going slower, so it's going to travel less. So if the blue car is traveling faster, the red car will have driven 0.5 times. How many times farther will the red car have driven than the blue car? 0.5 times as much as the blue car, half as much as the blue car. So on page 18, according to Kepler's law, the time it takes for a planet to go around the sun, also known as the planet's period, we'll use uppercase P for period, is related to the planet's semi-major axis. Sorry, it's off the screen there a little bit. There we go. Semi-major axis A, lowercase a, by the following formula. P squared equals A cubed. In a circular orbit, the semi-major axis is the radius of the planet's orbit. So A, we could have used R if we wanted. Planet A orbits the sun with a period twice that of planet B. Now, since planet A takes longer to go around than planet B, we already know that planet A is farther from the sun than planet B. Planet A has a semi-major axis of 1 AU. What is the semi-major axis of planet B? Okay, so here we have a diagram of what's going on. Because planet A has a period double planet B, it has to be exterior to planet B in its orbit around the sun. Okay, let's start with the formula. P squared equals A cubed. And we'd like to isolate A in this equation, so we're going to say A equals P raised to the 2/3 power. Okay, now planet A, that's the planet that we know. And planet A orbits the sun with twice the period of planet B. Therefore, planet B orbits with half the period of planet A. So in front of this P, we're going to put 0.5. But keep in mind that it also gets raised to the 2/3. So in front of our A, we've got to put 0.5 raised to the 2/3 as well. And since the semi-major axis we're talking about is 1, this just turns out to be our answer. And I don't have that memorized, so let's use a calculator. We have 0.5 raised to the 2/3 power, and it gives us 0.62996, basically 0.63. 0.63, and that's the right answer. On page 19, we see that planet A orbits the Sun with the period half that of planet B. That means planet A will be the interior planet. Planet A has a semi-major axis of 1 AU. What is the semi-major axis of planet B? Well, right away we know it's going to be more than 1 AU. So again, start with P squared equals A cubed, isolate A equals P raised to the 2/3 power. And this time, let's see, planet A orbits the Sun with the period half that of planet B. So therefore planet B is going to have a period of double planet A. So we'll put a 2 in front of the period, wrap some parentheses around that to see that the 2/3 also goes with the 2. And 2 to the 2/3 multiplied by A, well, our A here for planet A is 1 AU. So 2 to the 2/3 is going to be the answer. Okay, so we've got 2 raised to the 2/3 power, and that's 1.5874, basically 1.587. That's enough digits, 1.587, and life is good. Okay, I'm going to leave you to do problems 20. It's very similar to the one that we just did. And 21, we haven't seen this method used with kinetic energy, but I think you'll get the point. So I'm going to leave you to do 20 and 21 on your own. Thanks for watching, and good luck.